Hello everyone, welcome back. In this lecture, we will discuss about Bragg's law. It is discovered by W.H. Bragg and W.L. Bragg. Actually, W.H. Bragg and W.L. Bragg are father and son. For their work, they also received a Nobel Prize. We are discussing such an important work. Right? Let's start. Before going into the Bragg's law, let us discuss about a few things about the X-rays and the interference of the electromagnetic radiation. X-rays are electromagnetic radiation, and these X-rays have a short wavelength in the electromagnetic spectrum, and the wavelength range start from 10 picometers to 10 nanometers. So very small wavelength. And if you remember electromagnetic spectrum, the highest energetic waves are gamma rays, after that X-rays, after that UV rays, after that visible. This is decreasing energy, and after that we have IR, then microwave, then radio waves. This is the energy increasing, and this is the energy increasing. This is lambda decreasing. So the X-rays are almost at the end of this side of the electromagnetic spectrum. So these are short wavelengths. Now, so we know that X-rays are electromagnetic waves. Like every other electromagnetic wave, X-rays also shows interference and diffraction phenomena. Let's see something about the interference of the electromagnetic waves. If two waves are said to be interfere, then those two waves should have a same frequency and the same wavelength, should move in the same direction. Then if those two waves are superimposed, we may have two different interference. One is a constructive interference, another one is a destructive interference. Let's see when a constructive interference can be possible and when a destructive interference can be possible. If you see here, this is an electromagnetic wave, this is a 1, this is a 2. And if you see here, these two waves are traveling in the same direction with the same frequency, with the same wavelength. And moreover, if you see, the phase difference between them is 0. That means they are in phase with each other. These kind of waves are called coherence waves. Now, if these two waves are superimposed, we get a resultant of these two like this way. This is the resultant of these two. Now, if you see here, when the phase difference is between the coherence waves is 0, then that means the crest of the one wave and the crest of the another wave exactly superimposing at the same time in the same position. Then the resultant wave amplitude will be the sum of the amplitudes of the first wave and second wave. If you see here, this is the amplitude of the first wave and the A2 is the amplitude of the second wave, then the resultant wave will have amplitude of A1 plus A2. Similarly, even the trough side also, we will have the amplitude of A1 plus A2. That means, when these kind of waves are interfering, we get the resultant wave with the highest amplitude, and the amplitude is equal to the sum of the amplitudes of the individual waves. So in this way, we get a resultant intense wave. Now, for example, if the two waves are interfering like this way, that means if you see here, this is the first wave and this is the second wave. In the first wave, you can see they are actually out of phase, exactly 180 degrees. Now, if these two waves are superimposing, what happens? Now, if you see here, here also the amplitudes will be added. But if you see here, if this is in the positive direction, this will be in the negative direction. Now the positive and negative addition gives us 0. So they both will be cancel each other. So we get a resultant wave like this way. Here you can see there is no wave at all. That is because these two are out of phase. When they interfere, we get a destructive interference. This is a destructive interference, and this is a constructive interference. This is a constructive interference, this is a destructive interference. Now, let's see other case of constructive and destructive interference. Here in this case, the phase difference is 0. Let's see what happens if the path difference exists. Let's see, these are the two different cases. Now, if you see here, this is the first wave and this is the second wave. And the first wave already started, and the second wave, you can see here there is a path difference between the first wave and second wave. Now, the path difference is lambda by 2. Then you can see here the first wave and second wave look like out of phase. Now, in this case, they both destructively interfere and gives us nothing. There is no wave at all. This is the resultant wave. There won't be any wave at all. But in the case, if you see here, if this is the first wave and this is the second wave, now the difference between the first wave and second wave, the path, that means the second wave started exactly after 1 lambda distance. Now, this is the path length, and the path length is lambda. Now, if you see here, if the path difference is exactly lambda, then we can see the both wave crust are matching each other. The crust is matching at the same time, same position. That means these two waves constructively interfere and gives us a maximum amplitude. This is the resultant wave. Now, if you see here, this is the amplitude, this is the amplitude, we get a high intense wave. That means if the path difference between the two waves is n plus half, we get a destructive interference. And if the path difference is exactly n lambda, we get a constructive interference. Right? So, when the phase difference is 0, we get a constructive interference. When the path difference is exactly n lambda, we get a constructive interference. If the path difference is n plus half, that means exactly half is difference, then also we get a destructive interference. That means we don't get any light out of it. So, this is about interference phenomena. The diffraction. Let's see something about the diffraction. Diffraction means bending of light at some obstacles, or when light is incidenting on the slit. This is a slit. The slit width, the light will only transfer through this slit only when the wavelength is comparable to the width of the slit. This is called a diffraction. Diffraction means bending of light. Here, when the light is incident on a slit, it will diffract through the slit. That is only possible when the wavelength of the wave is comparable to the width of the slit. Then only the waves can be diffracted. Once diffracted, they will constructively, destructively interfere, gives us as spots. Now, I will explain why I am discussing this. I will be using this in the next few minutes. Now, in order to get X-rays to be diffracted, we need a slit width of the order of wavelength of the X-rays. We know that the wavelength of the X-rays is of the order of 10 picometers to 10 nanometers. If you wanted to see X-rays to be diffracted, then we need to make a material with a slit width of the order of few nanometers. That is impossible to make. However, if you see any crystal, the distance between the two planes, that is the interplanar distance, is of the order of few nanometers always. Now, if we can use the crystal as a three-dimensional grating, then X-rays can be diffracted. That's what exactly W.H. Bragg and W.L. Bragg did and got a Bragg's law. Now, let us construct a crystal and send X-rays and then diffracted. We will get and diffracted, and we will see how the condition of the diffraction can be get. Let's see, this is the unit cell. We know that by using unit cell, unit cell is the smallest volume of the crystal, with which if you repeat this unit cell along the x-axis, y-axis, z-axis, we get total crystal. That smallest volume is called unit cell. Now, this is the simple cubic unit cell. Now, I am repeating this along the x-axis. Now, if you see here, when I repeat, and I am also repeating this along the y-axis. Now, repeat these unit cells along the xy plane to get the total crystal in 2 dimensions at least. Now, we got it. If you repeat these unit cells in the 3 dimensions, we get total 3-dimensional crystal. However, to observe the Bragg's law, I only restricted this in x and y direction. Now, we also have learned that in the crystal, there is equidistant lattice planes are available. You can see here, these are the equidistant lattice planes. For example, if we consider this is the y-axis, now these planes are simply 0, 1, 0 planes. And the distance between these two planes, lattice planes, is interplanar spacing, that is d. Now, we know that the distance between the two planes, interplanar spacing, is of the order of few nanometers. Now, if we incident X-rays on this crystal, then these X-rays can diffract from the crystal so that we can get information of the crystal. Now, let us incident X-rays on this crystal. This is the X-rays are incidenting. Now, the X-rays, if the diffraction condition satisfies, now the X-rays will be reflected from the two planes. I have considered this is the first X-ray, this is the second X-ray. Now, this X-ray is incidenting on this atom and then reflecting, and this X-ray is incidenting on here and then reflecting. Now, if you see the two waves are reflecting, we only see the reflection when the Bragg's condition is satisfied. And also, when these two X-rays are reflecting, they may constructively interfere or destructively interfere. We also know that the condition for the constructive interference, that is, the path difference is equal to n lambda. Path difference is equal to n lambda. Let us see the path difference between these two waves. Now, if you see here, the first wave and second wave. Compared to first wave, the second wave is traveling little bit longer distance until here, and also it is traveling longer distance in this direction. Now, let us find how much is the longer distance that the second wave is traveling compared to first wave. If you see here, until this point, both 1 and 2 are traveling at the same distance, and from here again the two waves are reflecting same distance. That means this distance is same, this distance is same. Now, the extra distance traveled by the second ray is from here to here and from here to here. Now, if this distance is equal to, that means this is the path difference that is traveled by the second wave compared to the first wave. If this path difference is equal to n lambda, then we can see these two waves constructively interfere and gives us a maximum intense X-ray, reflected X-ray. If the path difference is n plus half lambda, then we get destructive interference. That means though we incident X-rays on this crystal, we don't get any reflected X-rays. For convenience, we only have taken 2 X-rays, but in general, in a real experiment when we do, we have many X-rays like this way. Now, all these X-rays, when they are incidenting on these planes, they reflect like this way. Now, these reflected X-rays interfere either constructively or destructively, depends upon the path difference between them. We already discussed the path difference. If the path difference is n lambda, we get a constructive interference, and that is the condition for the diffraction. that is the Bragg's law. Now, let us see this in the 2 dimension and derive the Bragg's law. So, for this one, let us consider a 2-dimensional lattice planes. These are the two-dimensional lattice planes. For convenience we have taken. The distance between the planes is interplanar spacing is d. This is the interplanar spacing d. That means the distance between the 2 planes. Now, as we discussed here, this is the 2 X-rays. We only have taken 2, but there will be many more. But only we have, for calculation purpose, we have taken 2 and find the path difference. Now, this is the first ray and second ray. Now, we know that the extra distance traveled by the second ray is from A to B. That means A to B and B to C. Let lambda be the wavelength of the incident X-rays. Let lambda be the wavelength of the incident X-rays. Now, the condition for the constructive interference of the reflected waves is equal to the path difference. That is, the path difference is equal to, the path difference should be n lambda. From the figure we can understand the path difference is AB plus AB is from here to here, and the second ray is traveling again extra distance from B to C. That is B to C. This is the path difference of the second ray compared to first ray. That means AB plus BC is equal to n lambda. This n lambda is coming. We are considering that these 2 waves constructively interfere, and then we get a reflected X-ray. If they are destructively interfering, we don't get any X-ray. But our aim is to get the X-ray. The condition is path difference is equal to n lambda. Now, let us find out this AB and BC so that we get condition for the constructive interference in the Bragg's law. So, if you see here, when an X-ray is incidenting on the crystal, normally we consider angle between this is the normal to the surface. Normally we take this is the angle in the general optics. But in the crystallography, X-ray crystallography, we take glancing angle. The glancing angle is here. This is the angle. The angle between the surface to X-rays. Now, if this is the angle, this is also theta. And also if you see here, this one and this one is 90. This is a 90. And now, if you see here, this line and this line is also 90. So that means we can write, if this is the theta, then if this is a 90, then this will be 90 minus theta. Now we know that if this is a 90, if this is a 90 minus theta, then certainly this will be theta. Right? So now this is the theta, this is the theta. I'll erase all these things, I'll rewrite so it won't be confusing. So this is the glancing angle, and by using geometry we can get this is also theta. Now we need to get the distance A to B, B to C. So let's find out. So from triangle OAB, sin theta is equal to, we can write sin theta. Sin theta is equal to, this is a 90, this is a 90 degrees, so the opposite side is hypotenuse. That means OB is a hypotenuse. So sin theta is equal to AB by OB. So from this we can write AB is equal to OB into sin theta. Now if you see here, the OB is actually the distance between the two planes, that is interplanar spacing d. So we can replace OB by d. So AB is equal to d sin theta. Let's consider this is the equation number 1 and this is equation number 2. Similarly, we also need to find out the BC from this triangle, and after that we will substitute in this equation. Now from this is a theta, this is a theta, and now here this is 90. So from triangle OBC, sin theta is equal to, this is a 90 degrees, opposite to 90 degrees is the hypotenuse, and now this is the angle, so this is the opposite side of the angle BC. So sin theta is equal to BC by OB, opposite side by hypotenuse. So we can rearrange this. BC is equal to OB sin theta. We know that OB is the interplanar spacing, that is the D. That means D sin theta, that is BC. Let's consider this is equation number 3. Now we know AB, BC. Now we will substitute this AB, BC values in the equation number 1. Substitute equation number 2 and 3 in equation number 1. We know that the equation number 1 is AB plus BC is equal to n lambda. Now AB we know that is the d sin theta plus BC we know that is also d sin theta, which is equal to n lambda. That means n lambda is equal to 2d sin theta. This is the Bragg's law. Here n is order of diffraction. N is order of diffraction. Lambda is the wavelength of the X-rays. D is the interplanar spacing. And theta is a glancing angle. This is not normal to the angle, this is the glancing angle. Remember this. Glancing angle means the angle between the surface to the X-rays. This is the Bragg's law. This is the condition for the diffraction maxima. That means if the X-rays are satisfying this condition, then they reflect constructively so that we get a reflected X-ray. So what is the use of these reflected X-rays? Now if you know, if the reflected X-rays are there, that means this condition is satisfied. That means when we know the lambda, we can find out the D, that means interplanar spacing. When we know the interplanar spacing, we can find out the lattice parameter by using the relation D is equal to 1 by root of h square by a square plus k square by b square plus l square by c square. Once we know the A lattice parameters, we can find the atomic radius. See how many different parameters we can find out by using simple thing. That's the reason why this experiment got a Nobel Prize. Now let's start one problem on this. Let's see some problem on this. X-rays of unknown wavelength gives a first order diffraction at a glancing angle 20 degrees. With the plane is 212 planes of a copper having FCC structure. Find the wavelength of the X-rays if the lattice constant for the copper is 3.615 angstrom units. They are asking you to find out the wavelength of the incident X-rays. It was given that the Bragg reflection, the glancing angle and the first order reflection. So let's write, given that the glancing angle is 20 degrees and the order of diffraction n, this is the first order, so n is equal to 1. And the lattice parameter of the FCC, this is a cubic structure, the lattice parameter is given already, that is A is equal to 3.615 angstrom units. Now we need to find out the wavelength of the X-rays, that is lambda. So for this one, we know already from the Bragg's law, n lambda is equal to 2d sin theta. But we need to find out here the wavelength of the incident X-rays. But what are the other things that we need? D, interplanar spacing. Did they give anywhere interplanar spacing? No. But instead of interplanar spacing, they have given lattice parameter. So we need to find out the interplanar spacing by using lattice parameter. So let's find out the interplanar spacing. D is equal to, for a cubic structure, this is a FCC structure. So for FCC structure, that is a cubic structure, interplanar spacing D is equal to A by root of h square plus k square plus L square. Now we need to substitute the plane 2, 1, 2. This is a h, this is a k, this is L into this. So we get a D. After getting D, we need to find out the lambda. Let's find out. So D is equal to A by root of h square plus k square plus L square. Now let us substitute. A is equal to 3.615 angstrom units by root of h means this one, this is a k, this is L. Now h is equal to 2. H square means 2 square 4 plus k square, k is equal to 1. So 1 square 1 plus L is equal to 2. L square, 2 square means 4. So that means we can write 3.615 angstrom units by 4 plus 4 1, 4 plus 4 8 plus 1 root 9. So that means 3.615 angstrom units by root 9. Root 9 gives us 3, which gives us the value 1.205 angstrom units. This is D. Now we know the D. Now we need to substitute that in the Bragg's law. That is n lambda is equal to 2d sin theta, but n is equal to 1. So we don't need to put it. So lambda is equal to 2d sin theta. Then substitute D value 2 into 1.205 angstrom units. Sin glancing angle is given 20. So substitute 20. So we get answer. The wavelength of the X-rays is this. So in this way we can find out either unknown X-ray wavelength or unknown parameters of the crystal, right? These are the two assignments for you to work on yourself and understand the problems. So in this one, a beam of X-rays with a wavelength, the wavelength is given, is incident on a crystal at a glancing angle. The glancing angle is given theta. When the first order diffraction occurs, calculate the glancing angle for the third order diffraction. So here they are asking you, first you need to use n is equal to 1, lambda is equal to 2d sin theta. From this you can get D value. From the D, later you substitute in the Again, n lambda is equal to 2d sin theta. Now, for the third order, that means n is equal to 3. In this case, now you substitute 3 lambda is equal to 2 into d value, we will get it from here, and sin theta. Unknown is sin theta, so find out theta value. This is how you need to follow. Please do it. And here, in the third question, calculate the glancing angle at which X-rays with a wavelength of 0.549 nanometers are reflected in a second order from a crystal with an interplanar spacing of 0.423 nanometers. They are asking us to find out the glancing angle. And they have given the wavelength and also interplanar spacing. So this is a direct question. So you need to find out, this is the second order, that means n is equal to 2. It's easier, direct substitution, you can do it easily, right? Thank you.